right? So if someone couldn't watch it in live, then he can watch it offline. Okay, let's begin. So thank you to our hosts for today, which is ActiveFans. And it's nice to know that ActiveFans is a cool company that gives an opportunity to talk about stuff not related to day-to-day work necessarily. A little bit about me. So in ActiveFans, I'm a data scientist slash computer vision algorithm engineer. And in previous positions, I've done similar things in Huawei and in a company called RTC Vision. So this is my contact. If you want to contact me after the lecture, you can use this email. And this is the Hebrew slide. So there's always confusion around what exactly is a computer vision engineer.
I'm not sure we're seeing the slides you're talking about. I see only introduction to computer vision.
Yeah. Sorry, I missed a few.
Good.
Okay, so we spoke about that. And now let's see what is a computer vision algorithm engineer. Can you see the video? אתם רואים את המסך שלי?
כן.
לא שומעים.
לא שומעים. Okay, never mind. Never mind. It's not very important. It's an explanation from a friend of what is this profession actually means, but it's not very important. So let's dive right in. So recommended books for people who are interested in this. The first book is very complex, in my opinion. The second one is much better. It's a very modern book, and you can find a version of it online. It's not saying that it's a required reading, but it's nice. It's a book from one of the fathers of this field. Now let's see what are we going to talk about in this very long lecture. So first, we will do a short introduction. Then we will talk about what is computer vision and why it's hard. Then we will talk about brief history of development of this field, starting from inception up to these days. And finally, we will look at some practical implementations of the technology in different domains and fields and in ActiveFans as well. So I will show you what, towards the end, I will show you what we've been doing so far in ActiveFans. Okay, so let's start with an introduction. So this is a human, and the human is a very complex biological machine. It's very hard to say what a human is and what intelligence is exactly. But what we do know about is we know something, and what we do know is that approximately 500 million years ago, something happened. And what happened was that suddenly, out of nowhere, all these creatures appeared, different kinds of creatures. So this is called the Cambrian period or a Cambrian explosion. And the question is why? Why did it happen? Why at all suddenly so many different species appeared? And the answer is that during that period, animals developed eyes. So as animals developed their vision systems, the one that did had a very strong competitive advantage over the ones that didn't, because if you have eyes, you can come and eat someone and he doesn't see you. So this created like a boost towards this explosion of different species, and all of them had eyes, and we have eyes as well. So this mechanism is very powerful in terms of survival of animals and in general. Now we know that vision is not just our optical sensors, right? It's something to do with our brain that helps us understand that signal that we receive from our eyes. But this is not a lecture about neurobiology. This is a lecture about computer science. So the next logical question would be, what is computer vision and not human vision? And so the goal is to teach a computer understand what is on an image. And to us, to humans, it looks very simple. So you look at it and you see a train. But for a computer, it is just a very large matrix of numbers. Yeah, and it's not very clear what you do with this matrix. So this is called a semantic gap. So this is the difference between how humans perceive an image and how it can be represented on a computer. So the computer doesn't know that there is a train. It doesn't know anything. Okay. So the problem of computer vision, we can formulate it in informal terms. So what is to see? What it means to see? So to see means to know what is where, but just by looking. And this like informal definition was given by David Marr. He is one of the fathers of this field. Now, let's try to understand what it means, right? To see means to know what is where by looking. So there are two sources of information here about the world. There is semantic information and there is metric information. So all kinds of distances, angles, things like this. Now, okay, so what is semantic information? Let's look at this picture. What can you say about this image? What can we say? So we can say, something is wrong. Yeah, so we can say that it's a scene that was captured with a camera outside, right? And we can say that this is a city. And also we can say that this is like urban traffic because of the buses and the cars. And if you look at the hieroglyphs, you can say that this place is located somewhere in Southeast China. And from the portrait of Mao Zedong, we can make a educated guess that this is China. And just in general, if you've ever been to China and visited Beijing, you can identify that this is Beijing and Tiananmen Square. What else can we say about this picture? Just by looking at it. We can locate objects. So we can say that this is a face, a very important object. And these are buses, and these are flags, and this is some text, and this is a building. And these are all examples of important classes. Now, what else can we say? So we can identify regions or segments of the image. So for example, this is a segment of the sky, and the segments of buses, and the segment of building. If we can segment, so for example, sky like this, what it means is that a computer can process this region of the image automatically. So it can process the sky automatically, and because it knows the semantics. Okay. So even more strongly, we can extract some qualitative properties of objects. So for example, in this photo, like if you look at Mao, you can see that it's not just any Chinese person, any Chinese face, some random face. This is Mao Zedong. And from the buses, we can see that they're moving objects and they're rigid. They're not deforming as they're moving. And the flags, we can see that they are rigid, and they are deforming objects and constantly moving. And from the direction of the flags, we can say that there is wind in the picture, and the wind is blowing from right to left. We can also say that the sky is blue, and we can assume that this is morning. So you see what I did there? From this one image, a vast amount of knowledge was extracted. Okay, so this was semantic information. Now, metric information is all kinds of distances. So, for example, if you have a Mars rover, okay, so a Mars rover has to be autonomous. Why? Because it takes like 20 minutes for the signal to propagate from Earth to Mars. So it's 40 minutes to have a communication with it. So you cannot control it from Earth. It needs to control itself. So this is where metric information becomes very important, because it needs to measure where it is on the terrain. Now, computer vision is a wide field, and it overlaps a lot of other scientific disciplines. So it partially overlaps like neurobiology and computer science and signal processing and some math. But generally, it is when you hear people talk about it, they usually talk about it in three contexts. So either image processing, machine vision, and computer vision. So let's try to understand the difference between them. Image processing is you imagine you output an image and you perform some processing on it. So you blur it, or you sharpen it, or you resize it. Image analysis is taking a two-dimensional image and deducing some knowledge about it. Pattern recognition is an abstract, like mathematical field that deals with vectors. So images are vectors, and it can recognize patterns in them because they are vectors, but it's an abstract field. Now, computer vision is where historically the most interesting algorithms are from. And this is because the computer vision field is more mathematical, and like engineering kind of people, or photogrammetry kind of people, or machine vision kind of people, they're more farther from mathematics department and closer to engineering department. So they rarely hear about the new methods that come out. So this is why most new algorithms are from computer vision area. So this is about the definitions of the terms, etc. So why do we want to study computer vision? Well, first of all, it has a lot of practical application. So because we see that computer vision has to do a lot with automation of processes. So the salary of human beings, it rises all over the world, even in poor countries. So what this means is that it's getting more and more relevant to replace human work with machine. A machine doesn't sleep, it works 24/7. So this idea is very appealing. Now, second of all, it's a very interesting topic, because all the mathematical methods that you use have a visual meaning. So there is nothing better than seeing the result immediately of your work on an image. Number three, it's hard. It's hard, and a significant part of our brains is responsible for vision. And computer vision is considered to be an AI complete problem. It means that if we can solve vision at human level, it's very probable that simultaneously to this, we will solve the problem of artificial intelligence, which is very good, yeah, or very bad. It depends on perspective. So if you watch like science fiction films, it's very bad. So like probably some responsibility for the doomsday, it lies on this field. But in the meanwhile, it will be interesting, and a lot of interesting papers. Yeah. So why is vision hard? Why so? Vision is hard because images of the same objects, they look very differently under different conditions. So first of all, depending on the viewpoint, the object looks very different. So here is a statue, okay? And the same statue was photographed from different viewpoints. So we ask, what is a statue? A statue is something with two eyes, or one eye, or 1.5 eye, or it has hair, or it looks completely differently. And yet it is the same object. And now our brain is very good at this. But how do you teach a machine to understand? Second, we have illumination. So depending on illumination, objects look drastically differently. So on these three images, you see white penguins. But depending on the illumination conditions, the same penguin can look white or gray or black, and it's still the same penguin. Now, objects come in different sizes. So if you say a human is an animal, I don't know, of 1.5 meters, and this is incorrect, because some humans are 80 centimeters and some humans are 2.5 meters. And the same is true for all objects. So how do you deal with this? So some creatures, living creatures especially, they experience elastic deformations. So the body, it deforms. It's not a rigid object. And it's very hard to say from this image how many legs, 3 legs or 4 legs or 2 legs. The next problem is occlusion. So it's very often that we don't see an object in its entirety, but just a part of an object. And they sometimes even very paradoxical kind of parts, yeah? So even for a very strong machine, an algorithm, it will be very hard to say, like, what is the distance to this horse? One more problem is concealment. So it's not very relevant for active but it's still a problem. So some creatures, especially like tasty creatures, they attempt to be invisible. So and yet our vision can identify them, even though the color matches perfectly. So how do we do that? Our vision also fails sometimes. So if you like to swim, you know how easy it is to like step on something like transparent. Next, we have one. This big problem is the problem of movement. So during movement, objects get blurred. So from this propeller, it's very hard to say that we are talking about a bird's head. The final problem, not the final problem. One more problem is intra-class variation. So these are all chairs. Some chairs are with, I don't know, handles made of wood, and some are made with handles made of, sorry?
Armchair.
Yes, armchairs, yes. Sorry. Thank you. So some are made from wood, some look big, some are small. They look completely differently, and yet our brain recognizes immediately that these are armchairs. How can a computer know that? Next, we have this log of wood that we drew in Paintbrush. Now, this is a log of wood, but if we add a table to it, it suddenly stops being a log of wood and then becomes a chair. And this happens because context plays a big role in our understanding of the object. So by itself, it was a log of wood. But in the context of other objects, it changes its semantics. So we have local ambiguities. So if you have like a low resolution image taken from afar, it's hard to say what this is. It could be anything at all. It can be a bottle or a cell phone or a person or a car or a skateboard. So from a single image, it's very hard to say, but from the whole image, it's easier to say. So you see, this is a phone, this is a skate. So all any image tries to confuse us all the time, but it gives a lot of clues that we can use. And the task of computer vision algorithm developers is to try to interpret these clues and put them in some formal form in code on a machine. So what are these clues? So first of all, we have color. You know that if something is large and green, that it is probably vegetation. And if something is bright on a green background, these are most probably flowers, right? So color helps us. Next, we have shadows and illumination. So let's leave the color out of the picture. And let's leave just the grayscale image. Just by looking at it, we can estimate the depth of the statue. So a computer can be taught to do the same process, not as reliably, but still, you will get the correct three-dimensional structure. So casted shadows. If you look at this image, you could make the mistake of thinking that we're watching like a working prototype of a flying carpet. But if we remove the shadow, it's just a man sitting on the grass. So the shadow changes the semantics. Grouping. So we have camels here on this image. And each camel is just a camel. But the whole group of camels is a caravan. This is a different semantics from the camel. So how do we automatically do that? How do we know that this line of camels is the caravan and that there are 3 caravans here? Not trivial. Okay, so another clue is that we have is called the linear perspective. So as we move farther away from us, objects become smaller. So this helps us to estimate depth. So if something is very close to you, it will appear big, and if it's farther away, it will be very small. So this is a nice clue. What about texture gradient? So here we see Earth, and the Earth has a certain texture. And the lizard, it tries to conceal itself by mimicking the colors of the ground, but it cannot. Why? Because we identify it, texture is different. The color is the same, the direction of the lines is different. And not only that we can identify the lizard automatically, our brain can also identify this hole, which is the same illumination, same color, it's just a different texture. And our brain automatically focuses on this. Depth can be estimated by occlusions. So if one object occludes another object, we know that this object is farther away than this object, right? So bottom line, despite all these clues, vision is inherently an ambiguous task. Because it happens because different three-dimensional scenes give the same two-dimensional image. So in this image, it's unclear if we are seeing like Lilliputians next to a normal vegetable, or are these normal-sized people and the camera is just on the ground and there is something in front of it. So to interpret, to understand the scene, we need some prior knowledge about the structure and like physical properties of the world. So that's a big separate question. How do you encode this a priori knowledge about the world formally? But we need to understand that vision is a very complex, ambiguous task. Okay. Now let's look at a brief. Yeah, do you have like questions so far? Okay. So let's look at a brief history of the development of this field. So the history of computer vision, it can be traced back to Aristotle days, who it is considered he was the main inventor of camera obscura, the first device to create an image. And because we're talking about computer vision, so the first thing we need is a picture, right? So we can say that when the first image appeared that used the perspective projection, so the foundations of this field were laid. Now, the next record about vision, it comes from the work of Leonardo da Vinci. And he left his trace like in almost every area of science. And in his works, he described a device called the magic lantern. And it was said that it could fixate light. What he meant isn't clear, but it's very possible that he really invented something like this. So other works of measurements from images were made by another famous painter, Albrecht Dürer. In one of his works, he demonstrated a device that allowed using a ruler and a compass to measure sizes of objects by their image, by the projection. The first photograph appeared in 1825. The inventor Niepce is known to be the first photographer. First photos took a very long time to develop. So this photograph took 8 hours to produce. Yet this is the first photograph. So technology advanced very quickly from this point, and after when was 12 years. So after 12 years, so first practical useful photographs appeared. So this was like an early prototype, and first real photographs appeared. And 3 years after appearance of first photograph, in a symposium of French Science Academy, it was announced that measurement by photographs is the future of geodesy. So we can see that even then, people were thinking very innovatively and long-term. So they understood that measuring things from an image is much easier than measuring on actual terrain. After some time, the first speed shooting appeared. First, so this is this horse right here. So this is the grandfather of video. And the first movie on film appeared in 1888. It's demonstrated on the right. So this is the small fragment of the family of the inventor. And the author of the invention went missing from a train, the legend says, and his brother was shot and killed after patent lawsuit with Edison, with Thomas Edison. So it's a brutal inventor fight. After 7 years, CRT was invented. So for the first time, there appeared an option to form images from electricity and not in an analog fashion. Approximately about that time, people started to do stereo measurements. So the scientist Edouard Deville invented a special system. And it allowed simultaneously to receive 2 images, build a 3-dimensional model from them, and then to do measurements on the model. So essentially, we can say that the first 3D movies appeared in 1896. And it was not a toy. It was used for actual measurements. There was an expedition to Canadian mountains, and they took stereo images with this device, and they built a detailed map of the terrain. At some time, first raster display was invented. So display was it was divided like to 2 separate elements by this time, 2 pixels. And inventor Philo Farnsworth. So if you watch Futurama TV show, you can remember this name. He demonstrated 60-line raster display, and it allowed to visualize all kinds of geometric shapes encoded in digital form. Now, considering that this is happening in the United States, who can guess what was the first symbol he visualized on the display?
A star.
It was a dollar. And the purpose for which all inventors show their inventions. And he was correct. And everyone were happy, and they gave him a lot of dollars to develop the technology. Yeah. Next, during another important for computer vision field, and that is the appearance of computers. So modern computers appeared during World War II. And the first English computers were top secret. And like the British used them to crack German encryption machine. But after the war, computers became very publicly known. And in 1951, in MIT, so this is one of the main like cradles of computer technology, it was demonstrated a computer that could display text and graphics on a monitor in real time. So the computer's purpose was simulation of air flight and anti-air warfare systems. So there were symbols that represented like missiles and planes, and there is a dots that display a map. And the operator had a light pen that he could use to mark the desired objects on the screen and get information about them. So this technology, like predecessor of touch technologies that resurfaced many years later. Parallel to that, devices were created to match images. So these devices were not yet digital, but they were analog at the time. And they allowed to take a few frames. So for example, you have photos taken from an airplane, and you want to stitch them together into one huge map. So this device did just that. And later, based on these ideas, digital systems to match images appeared, and we are using this technology in Octafence in logo identification, actually. So we will talk about it. Next, in 1960, the first digital image of human appeared. And it was synthesized in Boeing Corporation. And so it is known as the Boeing Man. At the same year, 1960, we can say that computer vision field was finally formed. So the first dissertation from MIT by L.G. Roberts, Machine Perception of Three-Dimensional Solids. So as usual, professor posed the question to his student. And the professor was very interested in computer vision and artificial intelligence. And at the time, people were dreaming. So if you read like books, science fiction books of the time, people were dreaming that in a short bit, we will go to Mars and a computer will replace the humans. So the professor had the same dreams, and he gave his PhD student the task for the summer. So you need to teach a computer to see. And the student successfully, he failed the task. He worked on it for several years, and he built a system that could determine the relative location on an image of a few simple geometric shapes. So cylinders, like pyramids, these kinds of stuff. Regardless, it is commonly accepted that this is the birth of computer vision, and L.G. Roberts is considered to be the father of computer vision, so he is known for what is known as the Roberts filter for edge detection. A few years after the first digital images appeared, came the first computer game. So it was called Space Wars. It's not computer vision related necessarily, but since computer games are such a powerful driver of technological development in computers, it's worth mentioning this event. So this game took 200 man-months to complete. In 1963, first computer-aided design systems appeared. So it allowed to visualize three-dimensional objects on a screen and perform like simple geometric transforms. So rotations, translations. In 1968, the birth of virtual reality, the first virtual reality system. It consisted of a television system. So to the eyes of the user was projected a stereo image. And on the top were sensors that could determine the location of the human in the scene and controlled the visualization sent to the human, controlled the computer to visualize. After a few years, so this is the grandfather of Terminator, Freddy the robot. First robot with vision, with machine vision. So this robot could construct cars from blocks scattered on the table. And yeah, this is the first robot with machine vision. Now, we can say that starting from the birth in the 60s until the 1970s, the field of computer vision was formed. And at the same time, there was a merging of this field with the field of biology and neurobiology that explore vision, especially the parts that explore vision. So one of the main people in computer vision is David Marr, and he is, by education, he is a biologist. And what happened in the 70s, what he was trying to do is he was trying to build the model of the human vision. So he made a hypothesis which about how human vision works. And over time, we find more and more justifications to this hypothesis. So the hypothesis is that vision is composed of three layers. What is known as level vision, which is the identification of edges and segments. And then we have sorting by depth, texture, computation, illumination in the brain. And finally, on the layer 3, we have recognition of objects and perception of three-dimensional world. So this is probably like the most influential work in computer vision ever. And many researchers, they cried from the paradigm created by David Marr, no one can drive us out. So let's see, what else can we say about the field? Images in videos are everywhere. And thanks to miniaturizations and mobile phones, every person today can take so many photos and videos that he will never have enough time to look at them all. And that's very useful for learning algorithms, this fact. But this is outside the scope of this lecture. Now, this is a very, very quickly growing scientific field. It's very wide, and it has image enhancement in it, and searching for images on the web, and searching for duplicates, and recognizing objects, and video surveillance, industrial robots, and special effects in movies, all kinds of compositing and motion capture. And so these are also solvable problems by computer vision. Next, let's look at some practical implementations. So we had enough of history. Let's look at concrete examples. So images are everywhere. The trillions of images on the internet. About 3 billion images are shared every day. About 400 million images or photos are uploaded to Facebook every day. So, and even more images are not on the web at all. So medical images, security systems, aero and space images, satellite imagery. So it's a huge space to explore. Now, what practical systems were we able to create? Doesn't mean that this problem is finished. People are still working on these problems. But regardless, these examples are systems that work in practice and are being used by corporations. So one of the first systems that worked very well was identification of digits and symbols. For example, you want to identify a license plate on a car, or numbers on containers, or digits on letters, automatically identify. In 2001, a very cool algorithm was developed to detect faces. It is called the detector of Viola Jones. So detailed discussion of the algorithms outside the scope of our talk today, but it provided that 10 times faster. It was 10 times faster than any algorithm that existed before it to do the same thing. It could work in real time. So accordingly, since it was so simple, today this algorithm is embedded in every modern camera. The next natural application is, for example, you want to detect a smile so that the camera can choose the moment to take the photo automatically when the person smiles. Of course, you could say that detecting a smile on someone with black skin is much easier than detecting it on other races, but yet. Working very well is facial recognition and different sorts of biometry. So the power and efficiency of facial recognition algorithms can be illustrated in one very interesting story. So many years ago, came out National Geographic magazine, and in which they choose a girl from Afghanistan, and they posted a photo of her on the cover of the magazine. And many years later, the crew of National Geographic, it went to Afghanistan again. And they wrote an article about the women in a country at war. And they posted a different photo of a different woman. And one of the researchers, he saw these photographs and decided to conduct an experiment. So, are these two women actually the same person? And he scanned the two images with a good scanner, high quality scanner. And then he segmented the part of the image that corresponds to the iris, to the eye, the iris. And he conducted a comparison. And it turned out that the probability that this is the same woman is practically like 100%. So this is phenomenal coincidence, and it shows the power of what technology can do. Also in biometry, working very well systems that like have fingerprint matching, facial recognition. So this is practically embedded in every phone or computer at the moment. Yeah. So all kinds of cool services. So if you have like in Germany, you have you take a photo of a movie poster, it is recognized, and then you can see like the matching trailer, movie trailer. So tourist guides. So who is a tourist? He's someone who is there with you, and he looks at the things with you and explains about them. So just, you know, if you could take your phone and take a picture, you immediately get an explanation from Wikipedia. So yeah, so tourism. Another huge practical field are systems to autonomously control vehicles, or driving assistance, also known. So today, most car manufacturers, they include computer vision systems that identify things like pedestrians, other cars, or road markings. They can help park. So, for example, German cars, they can park automatically. Now, it looks something like this. So this is the vision system of an autonomous vehicle. So you see that it detects cars and objects, and it stops when it's too close to a car. A huge field is the movie industry. So, for example, creating three-dimensional models of actors in virtual movies. So, for example, model of Agent Smith for movie Matrix, right? So every scene you see here, all the Agent Smiths is not an actual person. It's a model. It's a digital model. Also, motion capture is used in the movie industry. So it allows to capture emotions and then visualize the model in a game or movie with same expressions. So it's also another application of vision. Computer vision is used in sport events, sport competitions. So if you've seen like sport competitions with overlays on them, so you have all kinds of lines and scores in the broadcast. In order to overlay them correctly, you need to understand where the field is, where everything is located, so that you can correctly overlay. In tennis, there is a system that has a camera and that allows you to determine if the ball was in the court or out the court automatically. This kind of systems. Now, all kinds of robotic systems. So Mars rover, we said, can stitch panoramic image, build a three-dimensional model of environment. So you can check the article about computer vision on Mars if you are interested to learn more. Robots. So different three-dimensional maps. Another example of computer vision systems, 3D maps. So virtual Earth, Google Earth, Photosynth system from Microsoft. This is Photosynth. So it allows to build from a large collection of photographs a system to easily traverse between them. So if you have a lot of photos taken by tourists in the same location, you could build an entire virtual city from these photographs, like walk through them. Yeah, 3D model from user images. So model of Coliseum just from images from Flickr of the Coliseum. All kinds of mobile laboratories. So imagine you have a road construction, yeah? So the road gets damaged and it's thousands of kilometers of road. So how do you determine where the damage is, how severe the damage is, and what is the amount of money needed to fix the road? So send a car that does that automatically. It drives through the road once and it computes. It sees and it computes. Kinds of video surveillance. So it starts from laboratory animals and ends on humans on the streets. So this is the same concept. Track someone, recognize it. Many kinds of problems. Text detection in images. How do you detect text? How do you understand this text? Kinds of math segmentations of people to change the background. So if you are using Google Meet or these kinds of applications, they have an option to change the background. So this is how it's done. First, automatically segmented, and the background is replaced. Okay, let's see. So we are coming towards the end, and we're also. I'm about to run out of time, so I will steal maybe 5 more minutes of your time to just show you what we are actually doing in ActiveFence and how it contributes. So we are solving different kinds of problems from the domain of computer vision in our team. The first one is logo identification. In algorithmic terms, it is known as feature matching and homography search. So we can identify currently numerous logos of different organizations, from Islamic terror organization, neo-Nazi organization, it doesn't matter. It's symbols that can be automatically identified in images. And as such, it's an indicator of whether it is bad content or good content. It is some semantics that we were able to extract. Next is near duplicate search on images and videos. So whenever something is verified and a person said that it is a bad content, there is a strong incentive to find that content later. You have a new content and you want to ask, is this content, we have it as verified or not? So in order to do that, you need to be able to search for duplicates of images and of videos. And we can do that. We have a mechanism to do it. Next is OCR. OCR is optical character recognition. So given an image or a video, the task is to detect text and transform this region of the image into actual text. So it helps us identify all kinds of watermarks writings. Next problem we're dealing with is called zero-shot classification. So I won't go into too much details about this. This is a very recent development, but it shows a lot of promise in terms of accuracy to replace humans completely in some visual tasks. So this is a very, very powerful tool. Finally, we have facial recognition. So it's obvious why it's useful. I want to find all kinds of terrorists, whoever you want to find, persons of interest. So this is work in progress, but I think it will be solved with good accuracy. I am done. So thank you for participating. If you want to ask me something, you can ask me now or write me in an email. It's
Thank you, Dimitri. It was
yeah,
really
sure.
nice. It was really
Sure.
good.
Thank you very much,
Thank
Deva.
you.
Thank you.
Thank you, guys.
Do we have some questions?
Yeah, sure. Go ahead.